Hello everyone. So today we got a surprisingly easy problem from the 1959 International Mathematics Olympiad. So essentially what this problem I think is really hard, except you know one specific trick. And that's the trick I'm going to teach you today. So the question is, prove that this can never be factorized. Like prove that there is no common divisor except 1 in both of these terms. So for example, if n was 1, then we'd have 25 over 17, and it's obviously you can't factorize that, and it's true for all positive integer n's. So what does it mean for something for you not to be able to factorize a fraction? Well, as I said, the greatest common divisor must be one of the two. So as I said, the greatest common divisor of 21n plus 4 and 14n plus 3. This is supposed to be equal to 1 for all n. And how do we prove this? Well, apparently there's a really neat trick to show this. To show that the greatest common divisor of any integers a and b, that is the same as saying that there exists two other integers x and y such that xa plus yb is equal to 1. So for example, if our a and b was 10 and 9 maybe, then it is quite obvious that 1 times 10 minus or plus minus 1 times 9 is equal to 1. And if we instead pick two numbers that have a common divisor, like 2 and 4 maybe, then it's quite obvious that any linear combination of the two, any integer linear combination of the two, cannot be 1 because they're both even. And so that is, of course, a simpler case. You can still pick two odd numbers that have a common divisor, but it'll turn out that you can never find such integers x and y. So then let's just plug this in. So this then claims that this is equal to, that we can say that there exists an x and y such that x times 21n plus 4 plus y times 14n plus 3 is equal to 1 for all n. And why we're saying for all n in this case is because we want to prove that its greatest common divisor is true for all, is 1 for all n. So we still have to keep the for all n. So let's just rearrange this expression. So what do we have then? Okay, we have 21x plus 14y times n plus 4x plus 3y. We want this to be equal to 1 for all n. This then, of course, means that, okay, here we have a coefficient. This needs to be 0 for this to hold for all n's, and this has to be equal to 1 for all n's, which it does, obviously, because it's not dependent on n. So therefore, we get the system of equations that 21x plus 14y is equal to 0, and we have that 4x plus 3y is equal to 1. And if you solve this system of equations by Gauss elimination, you will see that x being equal to minus 2, and y being equal to 3 works wonders. Yes, I think that's the right one, because then you get 8 minus 8 plus 9. Yes, exactly. So that's 1. So yes, this is the solution you get. So for just good measures, we might as well just plug that back in. So what happens if we just take this expression with our new functions, or sorry, this one right here? Well then, okay, of course, it doesn't matter. No, I'm not going to do that. So yeah, since we have proved that for every n, there exists an x and an y and a y such that this holds, then this means that the greatest common divisor is equal to 1, and therefore the fraction cannot be factorized. So as I said, a very special trick. I didn't know it yesterday, and I absolutely would not have been able to take on this question. I don't think so, at least. It seems just I have absolutely no idea what one would do if not use this trick. And if any of you guys have any ideas, then please let me know in the comments. So yes, that was everything for me. Hope you enjoyed the video. Check out the link in the description, and I will see you some other time. Bye bye.